Good morning, all. Today we have gathered here for the fourth annual memorial lecture in homage to Professor MC Valsakumar. Before I come to welcoming all the guests here. Let me just briefly introduce Professor MC Valsakumar to the audience. Most of the students may not be aware, may not know him in person. Professor MC Valsakumar was a renowned physicist and teacher from Kerala. He was a scientist at IGCAR, Kalpakkam, till he superannuated as outstanding scientist and head of materials physics division in 2012. Since then, he had been a distinguished professor at Hyderabad Central University and IIT Palakkad. He was a versatile researcher. Some of his seminal works on open quantum systems and statistical mechanics became landmarks in those subjects. His research interests spanned from quantum field theory to computational material science. He is also remembered as an inspiring teacher with deep understanding of different branches of physics and mathematics. Professor Valsakumar was an honorary member of Academy of Physics Teachers, Kerala. Since his sudden, unexpected demise in 2019, January, Valsa's family and friends put together an endowment fund with the Academy of Physics Teachers, Kerala, with the understanding that every year an annual memorial lecture will be conducted in theoretical physics. So the aim is to inspire new generations of students to research in theoretical physics. We have been conducting this memorial lecture for the past few years, and this is the fourth memorial lecture. Today our chief guest here is Professor G. Baskaran sir. He retired from IMSc, Institute of Mathematical Science, Chennai. Now he is a distinguished professor at IIT Madras and also at Perimeter Institute in Waterloo, Canada. Professor Baskaran sir has, when we approached him with this idea, since Professor Baskaran sir also knew Valsakumar sir in person, he was very glad to accept this invitation. And he also consented to come directly here, because for the past 2 years we have been conducting this memorial lectures online because of COVID outbreak. So after a gap of 2 years, we are conducting it in person mode. So Professor agreed to come here to deliver this lecture in person mode, and also we are also live streaming this event. So on behalf of all of us gathered here and on behalf of Academy of Physics Teachers Kerala, I cordially welcome Professor G. Baskaran sir to this program. Thank you. And Valsa's family, his wife, Leela madam is here, and his relatives are here. So on behalf of all of us, I welcome Leela madam to this event. Valsa's friends and former colleagues, Professor Sebastian sir, retired from IASc, and then also he worked in IIT Palakkad along with Valsa sir. Professor Sebastian sir and family are here. And Professor Babu Joseph sir are here. So I welcome all these great persons to this program. Welcome, sir. All the students and teachers of Cochin University Department, and also students from nearby colleges are here. So I welcome, on behalf of APT, I welcome all the students to this program. And I'm sure that Valsa's friends and colleagues and students all over the world are attending this YouTube live streaming. Every year, this event is, online events are jam-packed. So since all of them who are attending through YouTube live streaming, I welcome all of you to this program. So I invite Professor Shaji sir and Dr. Shaji sir to preside over this program.
Dear Professor Baskaran, respected teachers like Babu Joseph, KLS, Sebastian sir, and Namburi sir, and other teachers, and dear students, also family members of Valsakumar sir. This is the fourth MC Valsakumar Memorial Lecture being conducted here. The first lecture in 2019 was given by Professor G. Anandakrishna. In 2020, it was given by Debendra Sahu, and last year it was given by Professor V. Balakrishna of IIT, and all these were well attended. This time we have Professor Baskaran from IMSc. I knew Professor Baskaran and also Valsakumar sir from IMSc days when Valsakumar sir used to come to IMSc once in a while to discuss with Professor ECS version. And Professor Baskaran, I had many opportunities to attend his classes. And he is an inspiring teacher. Though he works basically in condensed matter physics, he works at a fundamental level where the techniques used in one field is applicable in fields like particle physics, and things like that. So a lot of insight we will get by attending his talk. So I'm not stealing his time. So I will invite Professor Baskaran to give this memorial lecture. Okay. Rashmi will introduce Professor Baskaran and then he will talk.
A brief biodata of this esteemed guest. Professor G. Baskaran is an Indian theoretical physicist known for his work on condensed matter physics and strongly correlated quantum materials. Baskaran is an emeritus professor of physics at Indian Institute of Mathematical Science in Chennai and holds a distinguished visiting research chair at the Perimeter Institute for Theoretical Physics in Waterloo, Canada. Recently, he became a distinguished professor at the Indian Institute of Technology, Madras. In 87-88, Professor Baskaran, along with Nobel laureate P.W. Anderson at Princeton University, developed the resonating valence bond theory to describe the behavior of high-temperature superconductors. Baskaran is also known for his discovery of emergent gauge fields in strongly correlated systems, predictions of P-wave superconductivity, and high-temperature superconductivity in graphene. In 1983, Professor Baskaran was the first recipient of the ICTP Prize awarded by the International Center for Theoretical Physics, Trieste, Italy, to young scientists in developing countries for work in physics and mathematics. He was a member at the Institute for Advanced Study in 1996. He was also awarded the Shanti Swarup Bhatnagar Prize by the Government of India in 1990. And in 2019, he was awarded the G.N. Ramachandran Shastra Award. It is with extreme pleasure we would like to welcome you, sir, for the talk. It is switch off here.
So where is the, okay, wonderful. Good. It works. So dear friends, family of Valsa, and my many friends whom I am meeting after a long time, and SVM Satyanarayana and Hari Krishnan and Reshmi for inviting me to give this talk. Really a pleasure to be here. I'm very happy that I could come here today and be with you. So it's very nice, as I said, to meet many friends here. I have been to Cochin University at least 3 times in the past. I don't remember when I came, but so today I'm going to talk about quantum matter, and this lecture is dedicated to a friend, Professor Valsakumar. I got this beautiful picture from the internet, and so when I forgot to thank Shaji for introducing me, and see this, when you are on the stage, you forget things and slowly become normal. Okay. So I will talk about my brief interaction with Valsa a little later. So let me tell about my institute, because there are lots of students here. I have to advertise about math science. Many people know about math science, but some of the students may not know. It's an Institute of Mathematics. It's a very small campus, about 60 faculty, 100 PhD students, and at any time we have about 20 postdoctoral fellows and visitors. We specialize on theoretical physics, pure mathematics, and computer science. It's a small green campus. For the sake of students, please have a look at the website. You may find some interesting programs there. You may find interesting faculty member with whom you may like to do some project or short visiting research scholar program. A variety of things, exciting things there. Then since I'm talking in Kerala, I'm trying to make my campus very green. It's a very small campus. It looks really like this. You can see birds and it's just 10-acre campus. This is a hut where we discuss and do theoretical physics. Then I'm also at the Institute of Technology, Madras, where I think some of you may have been there. It's a beautiful wooded campus. It was remaining forest in the big Madras, about 500, 600 acres. Half of it belongs to the governor of governor's estate is there. Rest half is IIT Madras. So they preserve the wildlife like monkeys and deers and beautiful trees and some rare species of deers. So I jokingly tell that students come to my office, sometimes monkeys also come, so we have good time. Okay. Then I also spend time at this beautiful place in Waterloo, Perimeter Institute of Theoretical Physics. I'll tell about it soon. It's a big green park, a little zoo nearby, very nice throughout the year. Okay, so I am telling this for a specific purpose. This is Mike Lazaridis. You may have heard about, since the audience is very general, I will talk about general things, not go to physics in depth or anything, just about general things and my aspirations and so on. So this is Mike Lazaridis, a billionaire. Apparently he wanted to do theoretical physics when he was young. Poor guy, he could only become a billionaire, not a theoretical physicist. So there was an opportunity. He met somebody who was very fond of theoretical physics, a theoretical physicist, but who could not get a job. So he gave him $100 million and asked him to start a theoretical physics institute. That's how Perimeter Institute of Theoretical Physics started about 15, 20 years ago. He has given a total of $400 million. He says theoretical physics in science is something that helps transform society. In fact, there are articles written by him. I encourage you to look at it. So, and there is also, for the sake of students, they have Perimeter Scholars International Program. If you finish MSc and if you are motivated students, and if they don't care about marks. Suppose you have done some research and your guide writes about it, then there is a chance you may get it. They select about 40 to 50 students from all over the world and give them intense training for 1 year. No examinations. Morning there are 3 lectures. In the afternoon they work out problems. A happy situation. No examination. So please have a look at the website. It's called Perimeter Scholars International Program. It's a very eclectic place. So of course, such people are there in India. A.C. Muthaiah in Chennai, Krish Gopalakrishnan from Kerala. In fact, Krish has given 250 crores to start Neuroscience Center at IISc, which is already functioning, and about 60 crores to IIT Madras for 3 chairs on brain research, and also he has started a new brain center at IIT Madras. So Azim Premji, Shunaraga, and also some money comes from. Why I am saying this is it's very important to realize that science has been helping society over the last few hundred years, and it is transforming society. So in some sense, it's the duty of people who have money to spend a little bit of money on unended basic science. So whenever I give a talk, I tell them that if you find a rich uncle or aunt, please tell them they have $1 billion, spend 1% of the money for theoretical physics or neuroscience, some basic science. It's very important to realize. So, in fact, this has been his mission. Mike Lazaridis, what he does, he collects rich people and convinces them that the money that you give for science will help society, maybe not in the next 10 years, but 100 years. So we always use this example of Maxwell, because many of your physics students, Maxwell, more than 100 years ago, put various known laws like Ampere's law, Gauss's law, Biot-Savart law, Faraday's law, together in the form of a differential equation using calculus. And then came the remarkable prediction of existence of electromagnetic waves, which he found by putting numbers travels with velocity of light known at that time. So a single work by Maxwell, namely Maxwell's equation and wave equation, opened up electromagnetic waves to humanity. So 20 years down the line, Hertz generated electromagnetic waves. 20 years later, Marconi, J.C. Bose started communication. Now the world is what it is. And people are watching my talk thanks to electromagnetic communications and so on. So because of that, Mike Lazardi says that people are indebted to theoretical physics, particularly. So we have to support it. So it's a very good argument. So I will encourage young people to keep it in mind, because I have met billionaires. Not all of them are interested in giving away money, because when it comes to giving away money, there are many forces in society to misuse money. Whereas money spent on things like theoretical physics is worth it. So anyway, that's what I wanted to tell. Now another wish. I'm in God's own country, right? Kerala is called the God's own country. I showed all these beautiful pictures because every place there is plenty of nature. So it's my wish that every educational institution all over India and the world should become green and become God's own campus, like God's own country, full of nature and life. I've been talking to officials also, because educational institutions are temples of learning. In Tamil Nadu and various places, temples are associated with something called topu. It's a natural grove where herbs and various things are there. So very special, rare species of things are there. So traditionally, temples supported sacred groves, be it in India or in China, sanctuary for rare species of plants, home for birds and so on. So I have been campaigning that schools, colleges all over India and elsewhere should become green. Like, that's why I call it as God's own campus. So I take this opportunity to tell you, and please think about it. So opportunities to appreciate nature's beauty and secrets should be there in the campus. And I'm feeling it in the last few years more because I'm in IIT Madras. It's a beautiful campus. You walk through that, you see big banyan tree, you see this, you see the birds, and there is a lake and so on. It's almost like being in Kerala. The question is, every campus should be like that. I think that's my point. I think if we all try, it will happen. Because particularly when we are destroying nature so much, there is global warming and so on, many of the small efforts, particularly from future of the country, people like young people like you, it will be very good. Okay, so this is the general introduction. And this abstract I gave, matrix, classic, quantum, and classical description, quantum mechanics. So I will just give you a random walk of these things in the next 40 minutes given to me. Please feel free to stop me when I am talking. Okay. So the way I got connected to Valsa, I have known him for a long time. We used to discuss. There was a beautiful article by Valsakumar. Shaji may remember. He was on gate theory of defects in the elastic continuum. So those of you are learning about crystals. So what are crystals? Periodic arrangements of atoms and molecules in three-dimensional space or in two dimensions. So there is a symmetry associated, namely translation symmetry, lattice symmetry, and so on. Now, nothing is perfect in the world. So if you take a sodium chloride crystal and apply pressure or do something, it will create defects. And some of the defects are like interstitial or vacancies. But they also produce something called topological defects. For example, you can imagine a plane of atoms getting inserted in a lattice. So if you look at the top, there are seven step, in the bottom there are 6. So there is an insertion. And this is called edge dislocation. And if you walk around, you'll find that there is a misfit vector which is called the Burgess vector. This is all something that we learn in our BSc and so on. Similarly, there are other dislocations like screw dislocation where it is shifted. So, in fact, many of the mechanical properties of materials that you see come from defects and their interaction. And Valsa wrote this very important review article, Valsa and Sahu, gauge theory of defects in the elastic continuum. Now, gauge theory is something that you come across normally when you do electrodynamics, because Maxwell's equations has electric and magnetic field, but then Maxwell himself found it's better to describe in terms of something called gauge variables, which are vector potential. So that was the beginning of gauge theory. And then with the advent of standard model and high energy physics and so on, gauge theory got elevated. Standard models have SU2, SU3 gauge theories and variety of quantum field theories associated with that. Many fantastic phenomena. What is interesting is, Valsa talks about elastic continuum and gauge theory of defects. And this particular paper, you may like to see this because this Bulletin of Material Science is an Indian journal. You can download it. So it talks about non-abelian gauge fields, which came into prominence in physics through standard model of elementary particle physics, through Young-Mills theories and so on. Homotopy theory, differential geometry, fiber bundles, very powerful and advanced mathematics and this are appearing in a very down-to-earth context. The strength of materials, how dislocations interact with each other, non-abelian gauge fields. So that's how first I started discussing with Valsa. In fact, I don't remember, Valsa came to Mad Science and gave a series of talks. I don't remember how many talks on this particular topic because we were also interested in gauge theory. Now this particular field is becoming, exciting developments are there. So here you have something called vector gauge fields, other called tensor gauge fields, of defects in very popular in the field of something called fracton physics. So young people may like to note it down. It's very simple, easy to understand. Very simple models, and then you play with them, not even quantum physics. And then Vijay Shanai, my friend, who is a professor at IISc, I think Vijay is from Cochin, his parents live here. So Vijay is doing wonderful work in tensor gauge fields. Recently, he developed tensor gauge field for paper origami. Suppose you fold a paper and make something. We are all familiar with origami, ships and so on. There is a gauge field in ocean associated with it. Maybe some of you should invite Vijay and ask him to talk about it. So that's how I got connected to Valsa. And as I said, Valsa, apart from this, has been doing many wonderful work. It's a pity that he is not with us, but his spirit continues. That's the more important thing. So science has been undergoing an unusually long and intense revolution in the last 100 years. We can partly attribute to the understanding of quantum secret of nature. You remember, there was science advancing with thermodynamics, various understanding of nature. At the beginning of like 1901 and so on, there was the beginning of quantum understanding of nature. So that made a big difference, and it really, the growth of science became exponentially, and we don't know where it is going now. So much development. So the revolutionary developments in the last 100 years can be attributed to our understanding of quantum science of nature. And if you look at the history of quantum mechanics, very fascinating history, not just one person. It was Planck who hypothesized existence of what is called Planck quanta. Then Einstein took it over. He tried to explain photoelectric effect using that. And Einstein got Nobel Prize for his work on photoelectric effect, not for general relativity or special theory of relativity. Then came Bohr. He looked at spectroscopy, spectral lines. He rationalized it using so-called stationary orbits, just an ad hoc hypothesis which worked. Then came De Broglie. De Broglie said that you see materials which are particles, but when you go to the level of electrons and molecules, they are also waves. So wave-particle duality began. Then came C.V. Raman, his discovery of inelastic scattering of light, and S.M. Bose, derivation of Planck's distribution, using identical particle nature, its speciality in quantum physics. Then came Schrodinger, he said that if there is a wave, there should be a wave equation, so he wrote down. So fantastic development. So it's a collective effect unique in human history. If you think about quantum mechanics, we are all standing on shoulders there. Everybody, without Planck, Einstein would not have done what he did. Without Dept, without Bohr, so everybody was standing on shoulders. So it's a collective effort, and also a forerunner to the collective character of modern science. Science, if you think about 200 years ago, they were conducted by science and experiments and by individuals belonging to some university or school. And then, of course, they communicated. Now it has become so different. It's extremely collective. So that's why it's difficult to identify a hero who can be called a hero because people depend on others' work. Okay, so this is something I wanted to tell about light and light. In the sense, quantum physics started here. That is, if you look at the intensity of light that is emitted by, for example, black body, the intensity as a function of wavelength, the long wavelengths can be explained using well-known classical statistical mechanics. But short wavelength, there is a big problem. There is a hole which cannot be explained. So this is where Planck hypothesized and wrote down a distribution, which is called the Planck distribution. And one of the most remarkable things is, if you look at the distant sky in the night, the microwave radiation is coming from there. And that is supposed to be the radiation coming from 3,700 years ago, after Big Bang. That radiation is still coming to us because the distance is very large from the end of the universe, basically. So these are apparently perfect fit to Planck radiation. That is, quantum mechanics started working 13 billion years ago. So experiments have shown us the quantum secret of nature. Then one thing that students should appreciate is that we learn Newtonian mechanics, classical mechanics, and so on. They make common sense. It agrees with whatever we do day-to-day life. So all the three laws of Newton can be rationalized rather easily, even by a person who has not gone to school. For every action there will be an equal and opposite action, and so on. Every body will continue to be in its state of motion unless it is stopped. It makes a lot of sense. However, when it comes to quantum physics, they are counterintuitive. For example, according to classical mechanics, I am inside this room, that's it. Then I can be outside this room after the lecture. But I can't be both. But according to quantum mechanics, it's possible. So, in principle, electron, like objects like electron, can be created in a state in which it's inside one atom or another atom, so it's delocalized. So there is a wave state. So that happens when its dipole wavelength is much larger compared to interparticle distance. And so very profound consequences called linear superposition and quantum entanglement, tunneling. Like according to quantum mechanics, there is a very small probability, but it's astronomically small, that I can go through the wall and go to the other side without breaking the wall. It's called quantum tunneling. And it happens with electrons routinely, with protons and so on. But with macroscopic objects, there is a probability it will happen, that there is a probability you may find me disappearing, but the probability is so small, it will not happen for practical purposes. So that is called quantum tunneling. So many phenomena defy common sense. So when it turns out, these quantum phenomena which defy common sense are at the heart of many of the properties that we see in the material world. So that is what gives a physicist the power now. Because he has got a handle. Even chemical engineers come to physicists to understand quantum mechanics. Electrical engineers come to him, and so on. So these are just, I don't know, there is a Schrodinger equation, there is a Hilbert space, there is a complex probability amplitude, superposition, entanglement, and so on. There are also, again, one of the power of quantum physics and the mathematics associated with it. It was Dirac and others, Bose and others discovered that there can be only two kinds of particles in nature called bosons and fermions, which was amazing. This insight came from a deep understanding of mathematics of quantum mechanics. So called, when you take the many-body wave function, and then if particles are identical. So when you interchange the wave function, can change sign or may not change sign. So they give two classes of particles. So it's a mathematics prediction of mathematics. when people realize that photons are light quanta or bosons, and electrons are fermions and so on. So many things came from, so quantum mechanics, stability of an atom, this is something very important for you to realize. If you take a classical charge, positive charge like a proton and electron, if you do classical mechanics, classical electrodynamics, eventually this electron will orbit into proton and there will be chaos. Everything, there will be radiation and so on. But if you take a hydrogen atom, it's stable. That's because it's in a stationary orbit. So that's why even stability of atom, chemical bonding, molecules, minerals, all these things come from. So I will skip these things and then I will, this is something important. So quantum mechanics is very important for students, not from understanding material, because many new developments are happening. For example, I will suggest you are fortunate to have these NPTEL courses. For example, my colleague, Prof. Valsakumar, who gave the last Valsa Memorial lecture, is very famous for his quantum mechanics courses. If you want to understand quantum mechanics, listen to his talk. There is also Umesh Vazrani at Berkeley, quantum mechanics related to quantum computation. Because I'm sure many of you are aware of the fact that we are becoming greedy. We don't want to replace my classical computer with quantum computer, which will be much far superior in terms of ability to do computation and fast and so on. So quantum physics is coming back in a big way. So there is also a very interesting course, it's called Qubit by Qubit, offered by all these famous quantum computer people. And they charge some amount, but if you are from India, and if they are convinced that you will benefit by this course, they give scholarship, free scholarship. So this is called Qubit by Qubit, fantastic course. Then this institute, Perimeter Institute, also has many teaching resources, and when you say quantum mechanics, the interference, linear superposition, there are demonstrations about it. So many resources are available. Okay, so to become an expert in some aspects of, you need not know all of quantum mechanics. This is something I remember when I was studying, because quantum mechanics book can be very big. There are many aspects to it. But people have achieved great things, particularly electrical engineers. For example, there is a person named Grover, it's called Grover algorithm. And then Peter Shor, called Shor, they are all electrical engineers. They didn't learn quantum mechanics the way that we are taught. All of quantum mechanics, they learned what is called matrix mechanics, which is one component, basic part of it. Play with few 2 by 2, 3 by 3 matrix, and they have almost got Nobel Prize. So this is a very important point. To become an expert in some aspects of quantum mechanics, you need not know all of quantum mechanics. You have some vague idea, but go deep into some aspect. And as my friend Simon, my colleague, says, quantum mechanics is nothing but matrix multiplication and playing with finite dimensional matrices for practical purposes, which all of you know, because you know linear algebra, eigenvalues of operators and so on. Okay, now I'm going to tell about how this quantum physics, when things combine together, many surprises come. And this is called emergence. So Aristotle is supposed to have said, the whole is more than sum of its parts. It's well known in science, literature, art, life exemplify this. Things combine together. Many unexpected things come. Particularly literature. Amazing. Just whatever number of letters we have in a language, we put them in various combinations. We have big literatures and so on. Similarly, music, art. So contents and components differ from situations, but continuous surprises. That's what makes emergence exciting. So another way of saying is, more A plus A is more than 2A. So I have a simple way of demonstrating it. In fact, if you think about it, it's a very serious thing. Suppose I have these two pictures like Newton's rings. This is A and that's A. So when they are alone, they are what they are. Superpose them. What do you see? Depending on your imagination, you can think of it like a butterfly with some wings flapping. Then make one smaller. Somebody said it looks like an insect crawling on water. Then put 3. You see a cat. So nobody would have imagined that by this combination something will emerge. Now you understand it. So this is called a Mayer pattern incidentally. So I'm sure that people like you can make it even meow. You can make it sound like a cat. So this is at the heart of the modern solid state physics. Very unexpected things happen when things combine. I will explain it with a few examples. For example, in biology it's well known because we talk to biology students, of course it's obvious because you have atoms and molecules, then you have solids, then you have DNA, protein, cells, myriad form of life, consciousness and so on. Now is this unique to biology? Because when you talk about emergence, people always think about biology, living things, very profound consequences. But it was Niels Bohr, there is a conversation between him and a very famous biologist. Niels Bohr gives the following example from physics to illustrate emergence. What he says is, okay, give me a hydrogen atom. I understand it well. Let me put two hydrogen atoms. What do I get? I get water molecule. Then let me bring oxygen. I put it, I get water molecule. Then I put few hydrogen water molecules together. Then I get clusters of water molecules. I get hydrogen bonding. Then put more, I get a droplet of water. Then I put more, I get big water. Then I freeze it, it becomes ice. Incidentally, ice has about 12 forms, different crystal structures, under pressure and temperature variation. Then you let water flow. Like if you look at the flow of water in a canal or in the river, when there is flood, it's turbulence. So, if you give hydrogen and oxygen separately, you cannot predict there will be turbulence. But there is a sequence of, finite number of sequence of steps which give you turbulence. Incidentally, I am talking about turbulence because turbulence as a physical phenomenon is described by what is called Navier-Stokes equation. Everybody knows that. But we have no way of finding the solutions of all of them and characterizing them. That's why it's one of the biggest unsolved problems because of turbulence. And there are profound mathematical connections between turbulence and various things. So, this is what Niels Bohr calls as emergence. Just a simple hydrogen atom and oxygen atom put together, even I don't bring life, just drop of water and ice, crystals, amorphous ice, and then I get turbulence. Okay. So this is very nicely illustrated at some point by P.W. Anderson, famous Nobel laureate. I happen to be fortunate to be his collaborator since '84 for a long time. He passed away a couple of years ago. He wrote a very famous article called "More is Different." Because there was a time in which, in fact, even among students, this attitude may be there. I remember when I was studying, if you are a bright student, you do particle physics. If you are not, you do solid state physics. That's the kind of thing, attitude that is there. But Anderson similarly research also. Many people did that only if you do string theory or high energy physics or field theory, it's something. Otherwise, it's all just applications. Anderson pointed out that is not true. If you look at science in its totality, at every level, there is something new that happens. It doesn't happen at a level of standard model or string theory. You just study defects, like the way I said. Many defects organized in an elastic medium, and you get emergent gauge theory. The same thing that is used in high energy physics. So, he exemplified it and gave comfort to condensed matter physicists, which completely changed the history of condensed matter physics. So, I encourage people to look at this article. If you do a Google, more is different, you will get Anderson's article free. And so, okay. Now I am going to just give you hard condensed matter. Like if you take carbon atom, just carbon atom, who would have thought that if you put carbon atoms together, you will get graphite, the most stable form of carbon, then very strong form, namely diamond, then 60 carbon atoms combined to give you C60 molecule, the football molecule, and nanotube. And in fact, if you talk to Sebastian, he will say he can make motors out of organic molecules and make them run on the surface. So, just thinking about carbon alone, will not tell you that you will get eventually carbon nanotube. So new things emerge because of combinations, and everything is quantum mechanical. For example, this comes because of so-called sp2 bonding, this comes because of sp3 bonding, and these are mixed bonding. So then you go to a more complex crystal, you have a crystal called lanthanum copper oxide, copper, oxygen, and so on. And this, under some condition, when you so-called dope it, it becomes a high temperature superconductor. It was a revolutionary development in '86, which got in place very soon. So now we are looking for room temperature superconductor. So again, the combination of various atoms in specific way, completely surprising to emerge, magnetism and various physics. And then you go to what is called soft condensed matter, put the atoms together, it's supposed to be a membrane protein. You have alpha, beta sheets and the alpha helices and all kinds of things. These are condensed matter. And then let's go a little further. The same chemical bonding, hydrogen bonding, and some quantum mechanics leads to a little light, a baby, blue whale, the biggest tree. It's all emergence when things put together. So nobody would have guessed that if you give me a bacteria, I can predict the existence of blue whale. That's wonderful things happen. Everything is based on DNA and RNA in this case. So if you look at science from this point of view, the importance of emergence becomes extremely clear. One has to respect that. So if you talk about solid state physics, many new things have emerged thanks to experiments and thanks to quantum mechanics. For example, so there's something called Fermi C. You may have heard about it in your BSc class or MSc. If you take copper as a metal, there are free electrons. And it has metallic property, it remains a metal. And then if you want to understand the resistivity as a function of temperature, you cannot explain the simple Drew-Bayes law, the classical theory of resistance of metals. And if you look at susceptibility, that is how the system responds when you apply an external magnetism, so-called Pauli paramagnetism. So you cannot explain it using simple classical physics. So people like Sommerfeld used Pauli principle, mainly electrons are fermions, and then when you find the ground state, it comes what is called Fermi C in a momentum space. And then many things followed. The entire field of metal physics is still dominated by the physics of Fermi C. Similarly, superconductivity, free Bose gas, harmonic lattice, variety of things emerge just from combination. So that's why emergence, A plus A is not equal to 2A. That's very important. So I am just enumerating. Please tell me when I should stop. Shaju, how much time do I have? 15 minutes, good. I will. So, I have been involved in this field of strongly correlated system, which essentially it was there already. It came in the context of high temperature superconductors and fantastic developments. The notion of quantum number fractionalization, various anomalous quasi-particle, Majorana fermion, conformal field theory, Chen-Simons theory, K theory, ADFT, all the developments in string theory are useful here. So some of you may be mathematically minded. You may enjoy getting into these things. Fascinating things are happening. That's where they call it web of science. Science is never alone. This corner is connected to some remote corner. Like one of the famous examples is, you may have heard about Higgs particle. Peter Higgs got Nobel Prize a few years ago. That's called God's particle because that particle is responsible for giving masses to elementary particles. And some people call it as Anderson-Higgs particle. Because it turned out P.W. Anderson, whom I talked about, discovered a phenomena in superconductor, not at the level of the elementary particle, which he developed a theory which immediately Peter Higgs identified it as something very important and applied it to elementary particle physics. Unconnected things, you take a piece of lead, which is superconductor at 4 Kelvin or so, and then you have elementary particles like quark, electrons, and so on. The understanding of this leads to understanding of mass of elementary particle. So that's why science is connected. Like you talk about red spot of Jupiter. That is related to the vortices that you see when water flows. But scales are different and size are different. Yeah. So bosons and emergence. So if you take, I talk about Fermi sea, similarly bosons, amazing things happen. For example, we are all enjoying laser light. This is supposed to be some kind of condensate state, post-condensed state of photons, coherent states, and so on. So all these emerged from quantum mechanics, and there is a whole field of superfluid helium-4, quantized vortices, and so on. So, as I already told you about carbon atom, these two friends got Nobel Prize for understanding graphene. Already I said about graphene. Now, it's very easy for you to, with some basic understanding of quantum mechanics, to work out electron dynamics in graphene. Very easy. If you know a little bit of band theory. And many things happen. I wanted to show this because this is again emergence. See, if you take carbon atom, there are 6 electrons, 2 electrons in the 1s state, and 2 electrons in 2s state, and 2 electrons in the p state. So it turns out, because the 2s and 2p states are degenerate, in this case, you can form sp3 bond, as told by Linus Pauling decades back, or sp2 bond. So this is a diamond world. I am not going to. It's a rich man's world. Let me come to poor man's world, carbon. You have sp2, then that can form sigma bond and pi bond. From pi bond you can go to honeycomb lattice, and then there is magnetism at the edges, something like Dirac cone, and the chirality. All the concept that is there in high energy physics comes in a big way. There is something called Zitter-Bourg. If you do quantum field theory, if you look at Dirac electrons and so on, and if you look at the space-time trajectory of electron, there is a shaky motion. That's called Zitter-Bourg. It's very difficult to see it experimentally unless you go to super collider. Since the mathematics is similar in graphene, you can observe Zitter-Bourg in graphene on the tabletop. Phenomena similar to that. And for example, Vinny Lucas, who is from Kerala, I think Vinny is in the US now, he was a PhD student. Shankar, Vinny and myself, we showed that relativistic effects, which are very difficult to see in reality, because unless you know the velocity of light, you can't see it. But because the mathematics of electron dynamics in graphene looks like relativity, we found analog Lorentz boost, time dilation, and so on. This is a work with Vinny. So, this is amazing. That is, you put things together, unexpected things emerge, and these unexpected are distant connections. It's connected to what's going on in the stars, it's connected to what's going on in strings, and so on. So, this is this article is there in a book edited by, you can download it from this, or you can write to me if you want. So, this is something fascinating in science, the web of science, particularly in physics. So many things get connected, and they give new ideas for quantum computation or modern nanotechnology and so on. Okay, this I keep doing. Sorry, and this is a work that with Vinny Lucas. Now, having said that, let me finish with the hydrogen atom. Nothing more, just take hydrogen atom. What is emergence? So, hydrogen atom forms molecule. So, you apply pressure. Wigner predicted that it will become metal and very high pressure, because the pressure will be so much electrons will get liberated from the proton and will form a metal, and it never happens. So far, it has not been seen, because look at hydrogen and the pressure. What we find is fascinating things happen. There are many structures. The metallic state that we anticipated and corresponding superconducting state has been never realized, but something surprising happened. For example, hydrogen forms graphene-like layers with hydrogen molecules in between. Totally unexpected. Now, of course, we can rationalize these things since the experiments have come. So again, emergence is fascinating. and it has implications to the field of superconductivity. This is a timeline. Mercury was made a superconductor in 1910 by Cameron. And slowly, new superconductor, there is a big jump in theories also. And this is the diagram about how the transition temperature of superconductor varied with discovery of new superconductor. There was a quantum jump. Now there has been a new quantum jump. What people did was, they took hydrogen-rich material, not just hydrogen alone, like lanthanum hydride, LaH10, and applied pressure. It has become room temperature superconductor, but under great pressure. So, this is the fascinating thing. That is, hydrogen molecule has a property, put them together, they have a different property. Applied pressure, they will know different property. So, I can tell any number of such examples of emergence, and there are many, many things. And I have, this is really, you will remember, last year's Nobel Prize was given to Parisi, a physicist, and two climate scientists. This is a fascinating example of emergence. So, because Parisi was trying to understand how spins in a metal interact and behave. Let me directly go to that. So, we take copper. We put a small percentage of manganese atom. You know, manganese atom carries a magnetic moment. So, they are randomly positioned, and their behavior was not easy to understand because it's not a ferromagnet or antiferromagnet. It's called a frustrated system. It's like a glass. The spins don't know which way to point out because two neighbors say that if please point parallel, let's be parallel. Other neighbor says let's be anti-parallel because the coupling is ferromagnetic or antiferromagnetic. So, in order to understand this gentleman, my Professor P.W. Anderson and Sam Edwards wrote down a model, just a simple model, mathematical model, to understand just dirty copper containing some manganese impurity. And then it led to fantastic development, including Parisi solution, which gave ideas for brain theory. Now, these, as I said, things are connected. So these people are trying to understand collection of spins that are interacting in a metal. In a metal, like these spins are like impurities, they are randomly there. And then a deep theoretical understanding, thanks to Parisi and Edwards and Anderson and so on, gave me the idea about how brains function. This is where John Hopfield came. He said, if you want to understand brain as a theorist, I'll make simplifying approximation. If you look at the neuron is either firing or not firing. But if you look at in detail, there will be detail. He said, no, let's forget about it. Then he said, this like spin up or down, two-state. When one neuron, physiologically, when it is firing, it is connected to another neuron through what is called an axon. Depending on the connection, this neuron tells that you also fire. With some neuron, it says you don't fire. So it's called excitatory inhibitory. You put them together, that explains many of the associative phenomena, memory of brain. So unexpected connection from condensed matter to brain theory. So I can keep on telling you these things. So I just wanted to complete my talk by saying that quantum physics is important in the material world, also in some instances in biology. And a deeper understanding has led to profound developments elsewhere, unconnected with what you are studying in the lab. You may be doing some nanomaterial or composite material, but it has given to understanding elsewhere, completely unconnected place. So it's worth exploring, and I will, let's see, what do I have? So my colleagues are working on it. Okay, I think I'll stop here. I'm very happy to answer questions if you have. I'm sorry for a random walk, but I can't do more than this in this time. But I hope you take the message and please go and read some of these things. Thank you very much.
Now students can ask questions to Professor.
See, I have a habit. If nobody asks a question, I will not leave the room. I will be here. So you have to ask the question. And I know that Kerala students are more shyless than Tamil Nadu students. In Tamil Nadu, it's terrible. Nobody asks questions. They'll be smiling and sitting. In Kerala, I find students ask questions. So please. You can ask any questions.
Sir, can I ask a question? Okay.
Please, yeah.
Since you mentioned ADF-CFT in your passing slides, I have also heard about SYK model and this emergence and holography sort of. Could you explain a bit more about it?
Very good. It's a good question. See, there is a model called SYK model. Such day, A and KTA. I'm very fond of that model because in some sense we planted a seed for that model. I told you P.W. Anderson, the picture. So he developed resonating valence bound state theory. So where spins are coupled to each other. So we were all trying hard to do real systems. Then came such day and A. So they wrote down a model which looked unrealistic, but at the same time it was exactly solvable. And it was lying there in the paper, not many people respected it. Then came KKA. He simplified the model and he found out this model has a message to high energy physicists and to quantum gravity people. You see the connection, a dirty spin glass, a piece of rust. If you want to describe a piece of rust, you can use the spin glass model. That has a message to how black holes thermalize, information paradox and so on. That's what he's calling. So, careful analysis of models inspired by condensed matter physics is helping high energy physicists. This SYK model can be proved because Subir is an Indian, such day. So this model has got more attention than any other model in the past. David Gross, a Nobel laureate, has written 3 papers. Ed Witten, a Fields medalist, has written many papers. Because it's a very simple model. For a person experimentally motivated, it may not look attractive, it looks very unrealistic. But however, it exemplifies something in an unexpected corner, namely how quantum black hole behaves and so on. So it's a good question. So yeah, it exemplifies emergence. It's also a very important message that as some of you may be doing research and so on, try to construct models that are exactly solvable whenever possible, because nothing is trivial. If you can solve it exactly, there will be some use or other later. Yeah. Any other question?
Senior people can also ask question, right?
Unless the junior people object. But you are all junior to me.
Yeah, what I want to know is it the behavior, quantum behavior or behavior due to complexity? Can you clearly distinguish that?
Yeah, very important. So there is complexity in classical mechanics, many things, including chaos. But when quantum combines, the complexity increases exponentially. Completely unexpected feature comes. That's the point. Thanks for this point. So as Ramesh Babu says, if you think of Newtonian mechanics, even three-body problem is not solvable. There are chaotic solutions, and chaos is a complexity. There are fantastic regularities behind chaos. So this is the realm of classical world. But once you go to quantum world, because you enter Hilbert space, you go from phase space to Hilbert space, and new phenomena like quantum interference comes. So there are many fold. That's the point. Yeah. It's not unique to quantum physics alone, but quantum physics seems to make it much richer.
One more
Yeah.
technical thing. You said about gauge fields in defects, right?
Yeah.
What exactly is?
Very good point. So, for example, in the electrodynamics, if you look at Maxwell's equations, in general there can be electric charge or magnetic charge. So there are also gauge fields associated with it. So electric charge is a source of electric flux. So this is where even gauge theory comes. Now, when you look at the elasticity theory, continuum theory, if there is a defect, like a point defect, like a edge dislocation, then do a theory for it, it becomes a line of some emergent gauge field, which is an SO3 gauge field. So I encourage you to look at Valsakumar's paper, how gauge theory comes in elasticity theory. And it's not even gauge theory, it's SO3 gauge theory. And the fiber bundle concepts and all the concepts that are used in non-abelian gauge theory comes here. So another way of saying is, that if you have charges, there is a long range Coulomb interaction. So if you take a solid, elastic solid, create two defects, topological defects, there is an elastic force which is long range. So that already hints you there could be some gauge fields behind it. That's what they found out. Yeah. Once the article is well written, detailed article.
Okay, thank you.
I would like to know that the developments that is taking place in between the neutron stars and compact objects and the condensed matter. For example, superfluidity in compact neutron stars have been discussed in some of the books. So I would like to know more about
Very good. Thanks. So, what's your name?
Vishnu.
Vishnu is asking, see, neutron stars are stars that are too far away. But how do they radiate radiation, pulsars and so on? Now, according to theory, all the electrons have gone out. Basically, it's a neutral, at least the surface contains neutrons of very high density. And according to theory of superfluidity of helium-3, these neutrons will form a superfluid. So, theorists have hypothesized that if you want to understand the property of neutrons, stars, you have to invoke superfluidity of paired neutrons. So that's a very important, yeah. Let me complete.
Here, not electron found, there are two proton and neutrons.
Yeah, exactly. So it's not electron phonon. Even proton has become neutron because it has charge given away its charge. So the surface is supposed to contain only a thin layer of neutron, but these neutrons undergo superfluid condensation. The application is amazing. And occasionally people found that these neutron period changes, they are called neutron period glitches. And there was a paper by Anderson, Pines, Ipar and three people saying that this is something that you see in vortices in superconductors. Suppose you take a superconductor like lead or aluminum, you apply strong magnetic field, they form what is called quantized vortices. Now if you apply some perturbation to these vortices, it reacts like an earthquake. So this is called neutron star quake. To explain, there was a quantitative theory and so on. So it's an important question. What we see as superfluidity in helium-3 is supposed to be fermion because of theory at extremely low temperature like half a Kelvin is talked about in neutron stars where the Fermi energy is extremely high. Yeah. So it's a very important, the solid state that we do here is applicable to the understanding of surface of neutron stars, and there are many more things. Yeah.
Secondly, I want to know about the black hole has an event horizon.
Yeah.
So, is it related to condensed matter? Can it be?
Yeah.
Because there is a
Very good. Thanks. I had a student named Akbar Jafari, who is a professor at Iran. He has been working on this kind of issue. So, black hole, if you think about it, has something called event horizon. That is, in some sense, below the horizon and outside they are disconnected. No information going, and lots of, I'm not going to read it. So there is a whole lot of people who talk about analog black hole. That is, mathematical analog of black hole in the laboratory. So there is something called phosphorine and various organic materials where you have so-called tilted Dirac cone. So their event horizon has been invoked. If you do Jafari event horizon, you get a Google. So this is very interesting, that quantum gravity, even gravitational waves, with so much effort you have seen it. But in an analog situation, you can create gravity wave very easily, gravitational wave, analog of that. By the way, there is a book by Volovic called Seeing the Universe in a Drop of Liquid Helium. You may have heard about the famous statement of Byron, the English poet. He wrote a poem in which one line is that says, seeing the universe in a drop of water. So what Volovic says is, you take helium-4 or helium-3, they are so-called quantum liquids. And a deeper understanding of them theoretically gives you understanding of quantum gravity, SU2 standard model and so on. So it's a book called Universe, Seeing the Universe in a Droplet of Helium-4, Volovic. So analog gravity. So these are power of mathematics. Once you have similar mathematical structures, things have to be the same. For example, if you look at the graphene work that we did, you have mathematical structure like relativity, but instead of velocity of light, we have a smaller velocity, in the Fermi velocity. So to that extent, things are simpler and you can do it in lab.
Another question I have to, the cosmology, there's a Bose-Einstein condensate. So in that development, I would like to know. And fourth question is that is the connection between the condensed matter to the pure mathematics. Like there is a paper written in 1989. I had tried to read that paper by Witten and Atiyah, topological quantum field theory. So I would like to know those developments. That is, recently I saw Witten and Nathan said they were trying to write papers in condensed matter field theory. So I want to know about
Very good. So what Witten is like a high priest of string theory. So whenever he writes paper, people read it. Now, Ed Witten himself realizes that whatever they did in string theory, which in a very different corner, is applicable to condensed matter. In fact, he has, as you said, he's given a series of lectures how to understand condensed matter phenomena using ideas of string theory and vice versa. There are also some ideas going from here. And
so connection between black hole thermodynamics and the condensed matter systems, is there any connection?
That's what I said. That's called analog black hole. So you can create a situation like black hole in some quantum matter. That's called analog. Please look at analog black hole. So it's not perfect. Like this event horizon exists, but there will be other departures because many of these comparisons are at some level. Like I look at the sky, the clouds. Sometimes the clouds look like a tiger for a short time. So in the same way, you do something about some energy scale and time scale, it looks like what string theory is.
So Matt Weiser has worked in that, right? Matt Weiser. Sorry, Matt Weiser, New Zealand. Matt Weiser.
Maxwell?
Matt Weiser. There is a Matt Weiser. Okay.
So what is the name?
Matt Weiser.
I don't know. Okay, yeah. So I just have given you some glimpse of some of the things. So please go to internet because your times are very different. You can ask Mr. Google, he will tell you everything. In my time, you have to go to the library or go to friends and for books and so on. Now, many of these information, there are beautiful lecture notes available, YouTube and NPTEL and various things. So many of these things you can learn. So many of the questions you are asking is related to analog gravity.
So in general, in this hierarchy of sciences, quantum mechanics seems to be very crucial up to the condensed matter level. So what about the next level of hierarchy, like say biological systems, cells?
Next level?
Of this hierarchy, let's say consider biological cells or...
Oh yeah, very important. So people always thought that in biology, quantum mechanics stops at the level of bonding and some chemical reactions and so on. Now the scenario is changing. In fact, I have some slides later about quantum effects in biology. Very surprising effects. Because biology, as they say, is a warm, wet environment. Our brain or wherever it is. How can quantum mechanics be seen? But that's where nature seems to beat our imagination. So there is a whole field called quantum biology, where they invoke quantum effects in biological processes, including bird navigation. See, birds fly across big oceans. They are feeling small magnetic field, Earth's magnetic field. In terms of temperature units, 1 Kelvin. Room temperature is 300 Kelvin. So how can they distinguish? So people have said there is an entanglement in electron spin and nuclear spin. They can preserve this, and the whole story of bird aviation and quantum effect. Similarly, photosynthesis, light falling on plants, that involves quantum processes at room temperature, unexpected. So there are many surprises coming. That's called quantum biology. Just please do, many things are happening. But quantum biology has two branches. One is speculative. Please don't go into the speculative, because they will say consciousness is quantum mechanics and so on. Like Kuriji, they will start talking. But there are experiments done which needs quantum mechanics explanation. Correct. So there are isolated phenomena, but people are looking for collective phenomena through entanglement. Because there is a paper by Matthew Fisher, the very famous condensed matter physicist. He invokes nuclear spin entanglement in collective phenomena in brain processes. But it's just a beginning.
For entanglement, you need some kind of coherence and you need low temperature for that.
Exactly, that's the point. So, how do you do it? So, our nuclear spins are well decoupled from the environment. For example, it is well known that if you take nuclear spins in some molecule, if you put them in a singlet state, two nuclear spins, they will remain there for minutes. They don't decohere because they are very weakly coupled to the electronic path and lattice and so on. We will not. So there are situations in which you can keep the nuclear spin temperature at very low value, even at room temperature in a solid for a long time. So that is what is being used. So the quantum entanglement among electrons will get killed very quickly. Whereas with the nuclear spins, even long distances, that's Matthew Fisher has an article about Posner molecule. What he says is, we have a molecule which is there in some brain processing. There are two nuclear spins of phosphorus atoms, so they are entangled. When this molecule breaks into two pieces, one piece is here, and the entanglement remains. So when it collapses, this collapses. So, and so on. Many counterintuitive things happen because of nuclear spins. It's a very active, immediate future and very active field.
Any quantitative connection classical for the correlation in quantum time?
I do not know, but definitely when there is too much quantum entanglement, it looks classical. It's a very counterintuitive thing. When there is a so-called entanglement law, that is, if you take a system, quantum system, and you separate into two pieces A and B, and integrate A and B, then you can get idea about how the A system is entangled with B system. At low temperature, the entanglement is through the area. At high temperature, it's through the bulk. So when there is too much entanglement, it's almost classical. It's a very counterintuitive thing.
It's another navigation of birds, right?
Yeah.
Okay, so can this blocking and collective migration of birds be considered as a collective effect on biology on a function of birds and all?
I do not know about quantum biology, but the collective flock behavior of birds. In fact, Paris, I do not know if they have. Ah. So, he invents theory of collective behavior of bird flocks, because these birds, I should tell it in Kerala. See, we're all from Kerala. If you go to the hills, sometimes you'll find thousands and thousands of birds together, flying and dancing. It's called the bird flock. I have seen it not in India, but in Italy. It's amazing. Apparently, they do it to escape from the predator. And sometimes they take very strange shapes. They communicate among themselves. That's kind of instinct. And Paris has a theory about it, collective behavior. But whether quantum effects are playing a role, I do not know. So if you do bird flocking and the Paris, you will get good information about it. And I had some pictures, I don't think I have it here. By the way, see, in science, as I said, everything is connected. Paris is an amazing example. He started deep inelastic scattering theory, high energy physics, and then slowly came to spin glass theory and got a Nobel Prize, and he's doing many other things. So one person, I knew him very well, Giorgio. So, there are no boundaries. Like science and scientists have no boundaries. So please be open. Don't have fear of biology or psychology and so on. Okay. Now,
Hi, sir. So I had a question about Moire superlattices. So in graphene, you see high temperature superconductivity. So how high is the temperature? And I wanted to know how these Moire superlattices affect the superconductivity.
yes. So, she's asking, see, I showed you a picture of overlapping circles and got strange. So if you have just square lattice or honeycomb lattice and overlap them, you get strange periodicity. They're called Mayer periodicity. Now, recently, experimentally, they have found that if you put them together, unexpected conducting properties, because some of them become superconducting. But that is not the way to reach room temperature superconductivity, definitely. But unusual superconducting phenomena occurs there. Surprising behavior of TC and with angle, and surprising behavior with magnetic field and so on. So it may not give you room temperature superconductivity, but it will give you many other new insights. So that is being pursued. So, but then according to some theory, but in some theory involving Vijay Shana and myself and others, even if you take single layer graphene and go to something called optimal doping, it will become a room temperature superconductor. It has not been tested because it's very difficult to dope it at the moment. So Mayer is there is a lot of new physics. See, very often this new physics comes, as you say, at very low temperatures and so on. But then you learn and then apply it elsewhere.
So when you dope it, what is the dopant? Do you use a dopant?
So in the theory, we just change the chemical potential. But in practice, the dopant can be like suppose you take graphite and intercalate it with lithium, and lithium easily donates electron or other molecules. So we can do electron doping. That's where experimental complications come, when it brings in disorder and many other effects. So ideal dopant will be electric field, called gate doping, because that won't bring this. Then gate doping has a limitation in the sense how much I can dope, very low doping.
Thanks.
Okay.
Sir, I have one more question.
Sure.
So if you know about...
They may be hungry.
Yes, maybe this can be...
Please, sir.
Okay. So if you know about the emergent phenomena, let's say A and B are interacting and we get something more than A plus.
Correct.
So we know about what is more, but knowing that, how can we understand what was A?
That's an inverse question.
Yes.
It's very difficult.
Okay.
Very often, like if you look at turbulence, when you can ask, but just before turbulence you can go something. So that's why they say emergence is very surprising. At every stage something new happens, so you can't look back and say that what was there. So there are situations in which you can ask inverse question, but in general it's difficult, I believe.
So there is this idea by Peppenhaben where the gravity itself is an emergent property.
Correct.
So they try to write Einstein's equations as thermodynamic equations. So the
Correct.
question is, in thermodynamics, we have these atoms and molecules creating all these effects. So what about this gravity? So we try to, the question is reversing the process, right?
Correct, correct.
So, and it is not easy.
No, of course not. That is, Padmanabhan's work in thermodynamic theory. There are people who believe that, but then there are many questions which cannot be answered. And so, yeah. It's, back and forth is very, yeah. Inverse question in general is very difficult.
Okay.
Yeah.
So usually there will be a time scale for the emergence of various phenomena, right?
Yeah.
So is it just the interaction strength that determines this time scale?
Yes, many other things. For example, the time scales in turbulence is very different from the time scales in which hydrogen molecule or what proton tunneling. So it depends on the situation. Yeah, it's very situation dependent. I do not know if they have.
Usually if you look at social phenomena, it takes a lot of time for changes, particularly. And if the government takes some policy and people will blame that nothing is happening. I mean, is it
Correct, exactly, yeah. It may take astronomical time scale.
Yeah, in astronomy, you won't generally see any emergent phenomena. Astronomical time scale.
So time scale is a very difficult question. It's very situation dependent. Yeah. I can tell you privately about time scales in phase transitions and so on. Slowing down, aging in glasses. For example, a good question is glasses. Some glasses flow, you start with a good glass, over a few hundred years. Some glasses flow in 1 minute. So it's situation dependent. We also call that as glass. And some glasses flow in microseconds. Mathematically, they are all similar, but the parameters are different. Okay.
Any other questions? So Professor G. Baskaran will be available here in the afternoon, I believe. And if you want to meet him and discuss with him, please let me know, or Shaji sir.
You are most welcome. I am here to.
If no more questions, let me thank on behalf of Academy of Physics teachers and the Department of Physics. A big thank you, sir. Professor G. Baskaran, world-renowned condensed matter physicist. I also thank Valsa sir's family for joining and making this event happen, and all the dignitaries in the audience and all the students and all members. Thank you all. See.
So thank you Valsa's family for organizing this. Thank you very much.